To determine the appropriate electrical service size for a house, several factors must be considered, including heating, cooling, and appliance loads. The process involves several steps. Firstly, determine the heat load, typically measured in British thermal units, BTUs. This involves calculating the heat loss from the building, using methods like manual J calculations or specialized software. These methods consider factors such as insulation levels, window efficiency, and the specific climate zone in which the house is located. The result of this calculation provides the heat loss in BTU per hour. Secondly, determine the cooling load, also expressed in BTU. Similar to the heat load calculation, the cooling load is determined by assessing factors that contribute to heat gain within the building. Cooling load is often expressed in tons of refrigeration, TR. To convert tons of refrigeration to BTU per hour, multiply the TR value by 12,000. Thirdly, calculate the total load. This is achieved by adding the heat load and the cooling load together. The sum represents the total heating and cooling demand of the house and helps in estimating the maximum electrical demand. Fourthly, factor in the heat units and air conditioning units. Heat units, often expressed in kilowatts, need to be converted to BTU per hour for consistency in the load calculation. To convert kilowatts to BTU per hour, multiply the kilowatt value by 3,412. Add the BTU rating of each air conditioning unit to the total load. This accounts for the additional electrical demand from these appliances. Fifthly, calculate the amperage. This involves determining the voltage of the electrical system, which is 240 volts in this case. Divide the total load, expressed in watts, by the voltage to obtain the amperage. The formula for this calculation is amperage equals total load in watts divided by 240 volts. The resulting amperage value represents the minimum current carrying capacity required for the electrical service. Here is an example. Consider a house with the following characteristics: a heat load of 60,000 BTU per hour, a cooling load of 3 TR equivalent to 36,000 BTU per hour, heat units totaling 2 times 15 kilowatts, which translates to 102,360 BTU per hour, and air conditioning units totaling 2 times 3 kilowatts, equivalent to 20,400 BTU per hour. To calculate the total load, add the heat load, cooling load, heat units, and air conditioning units. 60,000 BTU per hour plus 36,000 BTU per hour plus 102,360 BTU per hour plus 20,400 BTU per hour equals 218,760 BTU per hour. To determine the amperage, divide the total load in watts by the voltage. Assuming BTU per hour is approximately equal to watts, 218,760 watts divided by 240 volts equals 911.5 amps. Therefore, the house would require an electrical service with a capacity of approximately 912 amps to adequately handle the combined load of heating, cooling, and heat units. It's important to note that this is a simplified example, and a comprehensive load calculation should consider various other factors such as lighting, appliances, and other electrical devices within the house. Consulting with a qualified electrician or electrical engineer is crucial for accurate load calculations and to ensure compliance with local electrical codes and safety standards. For more detailed and accurate calculations, consider using specialized software or consulting with professionals who can account for all relevant factors. They can perform a thorough assessment of the home's electrical needs, ensuring the electrical service is both safe and adequate for the intended use. Always prioritize safety and adherence to local regulations when dealing with electrical systems. Electrical work should only be performed by qualified and licensed professionals. When calculating the electrical service size for a house, one of the initial steps is to accurately determine the heat load. This involves a detailed assessment of how much heat the building loses to the external environment, especially during colder months. Several factors influence the heat load calculation. Firstly, insulation plays a significant role. The R value of insulation in walls, ceilings, and floors directly affects the rate at which heat is lost. Higher R values indicate better insulation, reducing heat loss. Secondly, windows and doors are critical components. The type of glazing, frame material, and overall construction of windows and doors impact their insulating properties. Single-pane windows, for instance, allow more heat to escape compared to double or triple-pane windows with low E coatings. Air infiltration, or drafts, around windows and doors also contributes to heat loss. Thirdly, climate zone is a significant factor. Different regions experience varying temperature extremes. Houses in colder climates require more heating, leading to higher heat load. Climate data, including average and extreme low temperatures, is essential for accurate calculations. Fourthly, building orientation affects heat loss. The direction a house faces influences how much solar heat it gains or loses. South-facing windows can provide passive solar heating during winter, while north-facing walls typically experience greater heat loss. Fifthly, the size and shape of the house influence the overall surface area exposed to the external environment. Larger houses generally have higher heat loads due to their increased surface area. Complex architectural designs with numerous corners and angles can also increase heat loss. Sixthly, ventilation rates affect heat loss. While ventilation is necessary for maintaining indoor air quality, it also introduces cold air from outside, increasing the heat load. Heat recovery ventilators, HRV, can help mitigate this by preheating incoming air with outgoing air. Manual J is a widely used method for calculating heat load. It involves a detailed room-by-room analysis, considering all the factors mentioned above. Manual J calculations can be performed manually using worksheets and tables, or with specialized software. Software solutions offer greater accuracy and efficiency, especially for complex buildings. The result of the heat load calculation is typically expressed in BTU per hour. This value represents the amount of heat that must be supplied to the house to maintain a comfortable indoor temperature during the coldest conditions. Accurate heat load calculations are essential for selecting the appropriate size of heating equipment, such as furnaces, heat pumps, or boilers. An undersized heating system will struggle to maintain the desired temperature, while an oversized system can lead to inefficient operation and increased energy costs. Consulting with a qualified HVAC professional is recommended for performing accurate heat load calculations and selecting the right heating equipment for your home. These professionals have the expertise and tools to consider all relevant factors and ensure your heating system operates efficiently and effectively. Remember that precise heat load calculations not only contribute to comfort, but also play a crucial role in energy conservation and reducing overall heating expenses. When determining the electrical service size for a house, accurately calculating the cooling load is as important as determining the heat load. The cooling load represents the amount of heat that needs to be removed from the building to maintain a comfortable indoor temperature during the hottest periods. Several factors contribute to the cooling load. Firstly, solar heat gain through windows is a major factor. Sunlight entering through windows can significantly increase the indoor temperature. The type of glazing, window size, and orientation all affect the amount of solar heat gain. Windows with low solar heat gain coefficients, SHGC, are more effective at blocking solar radiation. Secondly, heat gain through walls and roofs contributes to the cooling load. The R value of insulation in these built-in components affects the rate at which heat transfers from the outside to the inside. Well-insulated walls and roofs reduce heat gain, lowering the cooling load. Thirdly, internal heat gains from appliances, lighting, and occupants add to the cooling load. Electrical appliances, such as refrigerators, ovens, and computers, generate heat as they operate. Incandescent lighting produces more heat than LED lighting. The number of occupants and their activity levels also influence internal heat gains. Fourthly, ventilation introduces warm, humid air from the outside, increasing the cooling load. The amount of ventilation required depends on factors such as occupancy levels and indoor air quality requirements. Energy recovery ventilators, ERV, can help reduce the cooling load by pre-cooling incoming air with outgoing air. Fifthly, humidity levels affect the cooling load. High humidity makes it more difficult to cool the air. Dehumidification requires additional energy, increasing the overall cooling load. Sixthly, infiltration of outside air through cracks and gaps in the building envelope adds to the cooling load. Sealing these air leaks reduces infiltration, lowering the cooling load. Similar to heat load calculations, Manual J is a widely used method for calculating cooling load. It involves a detailed room-by-room analysis, considering all the factors mentioned above. Software solutions are also available for performing cooling load calculations. These tools offer greater accuracy and efficiency, especially for complex buildings. The result of the cooling load calculation is typically expressed in BTU per hour or tons of refrigeration. 1 ton of refrigeration is equal to 12,000 BTU per hour. This value represents the amount of heat that must be removed from the house to maintain a comfortable indoor temperature during the hottest conditions. Accurate cooling load calculations are essential for selecting the appropriate size of air conditioning equipment, such as central air conditioners, heat pumps, or ductless mini-split systems. An undersized cooling system will struggle to maintain the desired temperature, while an oversized system can lead to inefficient operation and increased energy costs. It can also lead to humidity control issues. Consulting with a qualified HVAC professional is recommended for performing accurate cooling load calculations and selecting the right cooling equipment for your home. These professionals have the expertise and tools to consider all relevant factors and ensure your cooling system operates efficiently and effectively. Remember that precise cooling load calculations not only contribute to comfort but also play a crucial role in energy conservation and reducing overall cooling expenses. The total load calculation combines the heat load and cooling load to determine the overall electrical demand of the house. This step is crucial for ensuring the electrical service is adequately sized to handle both heating and cooling needs. To calculate the total load, simply add the heat load and cooling load values together. Both values should be expressed in the same units, typically BTU per hour. If the cooling load is expressed in tons of refrigeration, it must be converted to BTU per hour by multiplying by 12,000. The total load represents the maximum amount of energy required to maintain comfortable indoor temperatures year-round. However, it's important to note that the heat load and cooling load typically do not occur simultaneously. In most climates, heating is required during the winter months, while cooling is needed during the summer months. Therefore, the total load calculation provides a conservative estimate of the electrical demand. In addition to the heat load and cooling load, other electrical loads in a house must also be considered. These include lighting, appliances, electronics, and other electrical devices. A comprehensive load calculation should account for all these loads to ensure the electrical service is adequately sized. The NEC provides guidelines for calculating the electrical load of a house. These guidelines specify how to calculate the demand factors for various types of loads. Demand factors are used to reduce the calculated load based on the assumption that not all loads will be operating at the same time. For example, lighting loads are typically subject to a demand factor of 100% for the first 3,000 watts and 35% for the remaining load. Appliance loads are subject to a demand factor of 75%. The NEC also provides specific rules for calculating the load of electric heating and air conditioning equipment. These rules take into account the size and type of equipment, as well as the climate zone. Once all the individual loads have been calculated, they are added together to determine the total calculated load. This value represents the minimum size of the electrical service required for the house. It's important to consult with a qualified electrician or electrical engineer to perform an accurate load calculation and ensure compliance with local electrical codes and safety standards. These professionals have the expertise and tools to consider all relevant factors and ensure your electrical system is safe and reliable. Remember that an adequately sized electrical service is essential for providing safe and reliable power to your home. An undersized service can lead to overloaded circuits, nuisance tripping of breakers, and even electrical fires. When factoring in heat units and air conditioning units, it's essential to convert their power ratings to consistent units, typically BTU per hour, to accurately assess their contribution to the total electrical load. Heat units, often electric resistance heaters, are usually rated in kilowatts. To convert kilowatts to BTU per hour, multiply the kilowatt value by 3412. For example, a 1.5 kilowatt heater produces 5118 BTU per hour. This conversion allows you to directly compare the heat output of electric heaters with the heat load of the house. Air conditioning units are often rated in BTU per hour or tons of refrigeration. If the rating is in tons of refrigeration, multiply by 12,000 to convert to BTU per hour. For example, a 2-ton air conditioner has a cooling capacity of 24,000 BTU per hour. When adding the BTU ratings of heat units and air conditioning units to the total load, it's important to consider their operating characteristics. Electric heaters typically operate at or near the rated capacity, while air conditioning units may operate at varying loads depending on the thermostat setting and outdoor temperature. The NEC provides guidelines for calculating the demand factors for heating and air conditioning equipment. These demand factors take into account the likelihood that these appliances will not operate at their full rated capacity simultaneously. For example, the NEC allows for a demand factor of 100% for the largest heating or air conditioning load, and 65% for the remaining loads. This reduces the calculated load based on the assumption that not all heating and cooling equipment will operate at the same time. In addition to the BTU ratings, it's also important to consider the voltage and amperage requirements of heat units and air conditioning units. These appliances typically operate at 240 volts, but some smaller units may operate at 120 volts. The amperage requirements determine the size of the circuit breakers and wiring needed to supply power to these appliances. The NEC provides tables that specify the minimum wire size and circuit breaker rating for various amperage loads. It is crucial to consult these tables to ensure the electrical system is properly sized and protected. When adding heat units and air conditioning units to the total load, it's important to consider their impact on the electrical service size. These appliances can significantly increase the electrical demand of the house, especially if they are large or numerous. An undersized electrical service can lead to overloaded circuits, nuisance tripping of breakers, and even electrical fires. It's recommended to consult with a qualified electrician or electrical engineer to perform an accurate load calculation and ensure the electrical service is adequately sized for the combined load of heating, cooling, and other electrical appliances. These professionals have the expertise and tools to consider all relevant factors and ensure your electrical system is safe and reliable. Calculating the amperage is a crucial step in determining the appropriate electrical service size for a house. Amperage represents the amount of electrical current flowing through the wires and is a key factor in ensuring the electrical system is safely and adequately sized. The basic formula for calculating amperage is amperage equals power in watts divided by voltage in volts. In this case, the voltage is 240 volts. To use this formula, you must first determine the total power consumption of the house in watts. This involves adding up the power consumption of all electrical loads, including lighting, appliances, heating, and cooling equipment. The power consumption of most appliances is listed on their nameplates in watts or amps. If the nameplate lists the amperage, you can calculate the power in watts by multiplying the amperage by the voltage. For example, an appliance that draws 5 amps at 120 volts consumes 600 watts. Once you have determined the total power consumption in watts, you can divide it by the voltage to calculate the amperage. For example, if the total power consumption is 24,000 watts, the amperage is 100 amps. It's important to note that this is a simplified calculation. The NEC provides more detailed guidelines for calculating the amperage of a house. These guidelines take into account demand factors, which reduce the calculated load based on the assumption that not all loads will be operating at the same time. The NEC also provides specific rules for calculating the amperage of electric heating and air conditioning equipment. These rules take into account the size and type of equipment, as well as the climate zone. Once you have calculated the amperage, you can use this value to determine the appropriate size of the electrical service. The electrical service size is typically expressed in amps. The NEC provides tables that specify the minimum service size for various amperage loads. It's important to select a service size that is large enough to handle the maximum anticipated load of the house. An undersized service can lead to overloaded circuits, nuisance tripping of breakers, and even electrical fires. It's also important to consider the future electrical needs of the house. If you plan to add more appliances or equipment in the future, you may want to select a larger service size to accommodate these future loads. Consulting with a qualified electrician or electrical engineer is recommended for performing an accurate amperage calculation and selecting the right service size for your home. These professionals have the expertise and tools to consider all relevant factors and ensure your electrical system is safe and reliable. Always prioritize safety and adherence to local regulations when dealing with electrical systems. Electrical work should only be performed by qualified and licensed professionals.